Today we are going to talk about Bluetooth Low Energy and its vulnerabilities. Are your Bluetooth Low Energy devices safe from hackers?
Yes, but actually no.
First, a bit of nerd nomenclature clarification. The folks behind Bluetooth weren't English majors, so their branding has caused a good amount of confusion historically. Bluetooth can refer to two very different protocols, Classic and Low Energy. Bluetooth Classic has a robust data rate to support throughput-intensive transmissions, such as audio. This is what your Apple AirPods and other proletarian alternatives run on. Bluetooth Low Energy, on the other hand, trades throughput for power consumption. It sips as little as 1% of Bluetooth Classic's drink, allowing devices to stay connected for months and even years on tiny batteries. Additionally, Bluetooth Low Energy also has considerably lower latency due to its lightweight nature. This is also why many wireless keyboards also use Bluetooth Low Energy. Bluetooth Classic and Bluetooth Low Energy are now marketed under the same umbrella term Bluetooth and can coexist on the same device, like your newest Android phone. However, these standards are not interoperable. In other words, Bluetooth Low Energy runs on an entirely different protocol stack than Bluetooth Classic. This video examines only Bluetooth Low Energy and its vulnerabilities. A wise man once said, "Know how it works before learning how it breaks." Let's see how Bluetooth Low Energy works. We'll occasionally refer to the phone as the initiator and a Bluetooth device as the responder. First, the Bluetooth device's manual tells you to turn it on and long press the pairing button to put the device into pairing mode. The device begins the connection setup process by sending advertisements. You then open the Bluetooth menu on your phone. The phone receives the advertisement and then sends a scan request. The responder receives the scan request and responds with a scan response. When your phone receives the scan response, it displays the responder's information on screen. You then select the device on your phone, which triggers the phone to send a connection request. This marks the end of connection setup. The two devices can now communicate with each other in plain text. However, for enhanced security, most Bluetooth Low Energy devices would initiate the actual pairing process by sending a security request. The phone responds with an affirmative, but to determine the level of security, they need to know what each other can do by exchanging their I/O capabilities and what each other wants by exchanging security requirements. The devices then enter the key exchange and authentication phase. It begins by both devices performing the elliptic curve Diffie-Hellman key exchange protocol and obtaining a symmetric key called DH key. By the way, the topic of public key cryptography used in this process is well beyond the scope of this video. You can learn more by doing a quick Bing search. Once the key is exchanged, the devices need to authenticate each other. Here's where device I/O capabilities and security requirements come in. Let's say we're pairing a Bluetooth keyboard to the phone. Now that they have the symmetric key DH key, the phone generates a random number that it asks the user to input into the keyboard. The keyboard then encrypts the number with DH key and transmits it to the phone. The phone then knows if the keyboard the user is interacting with is the intended device. If the responder device does not have a keyboard but has a screen, say your smartwatch, the phone generates a random number and encrypts it with DH key before beaming it to the responder. The responder then decrypts the key and displays the number on screen, at which point the phone asks the user to confirm that the two numbers match. If they do, then the phone knows that the device the user is interacting with is the intended device. If the responder device has no human I/O capabilities, such as your smart thermostat's remote temperature sensor, then encryption can still be established, but the phone cannot verify protection against man-in-the-middle attacks. Once the devices are authenticated, each device then calculates the long-term key and uses it to generate unique session keys for use in future communications. This marks the end of the pairing process. So now the two devices are paired, let's see how they communicate going forward. Say the Bluetooth Low Energy device wakes up and needs to transmit something to the paired phone. It first begins by sending advertisements as usual. The phone catches one of the advertisements and then sends a scan request and receives a scan response. Once the phone sees that the responder is within the list of recognized devices, it sends a connection request. The app on the phone then sends a read request on an attribute or data point. If the attribute does not contain sensitive information, the responder device could mark the attribute with simple read permission, which means the attribute or data point is transmitted in plain text regardless of pairing status. This could be something like a model number, for instance. If, however, the attribute contains sensitive information, then the responder device will mark it with encrypted read permission, which requires the responder to establish a secure paired connection before sending the requested data. In this case, the responder device uses the negotiated long-term key to generate a session key and uses the session key to encrypt the attribute before beaming it through the air to the phone. The phone then decrypts it with the session key generated from the same long-term key and sees the message. So, security seems pretty robust on Bluetooth Low Energy. Key exchange with asymmetric encryption, out-of-band verification to prevent man-in-middle attacks, and using session keys to ensure continual encryption integrity. On the surface, it appears that folks behind Bluetooth made it ironclad. But can we go deeper? In 2019, just a year before the world came to an end, this geek squad wearing white hats discovered a number of flaws in Bluetooth Low Energy's implementation on Android and iOS devices. You'll see how relatively trivially an attacker with minimal equipment can bypass the security measures and gain unauthorized access to Bluetooth Low Energy devices within range. Below, I list the 4 major design flaws that contribute to Bluetooth Low Energy protocol's vulnerabilities. I'll show you how these flaws can be exploited later. Design flaw 1. There are no mechanisms to specify a pairing protocol. For instance, when writing a companion app on Android for your Bluetooth Low Energy device, you use the create bond function to pair with the device. However, this function does not allow you to specify the device's I/O capabilities even though you have that information, since you made the device yourself. Design flaw 2. There are no mechanisms to obtain the negotiated pairing protocol on time. The call create bond is asynchronous, and the OS handles the actual pairing process. The app cannot participate in the pairing process until it completes. Design flaw 3. Android mishandles pairing errors. There are 2 issues here. First, if 2 devices are paired and the responder removes the long-term key by a factory reset, for instance, it sends an error code hex06 to the Android phone during the connection process. However, the phone does not notify the user of this issue, but would instead automatically communicate with the responder in plain text. Second, when an Android phone attempts to access an attribute with the encrypted read-write permission at the responder device, the device checks to see if the connection is encrypted. If not, the device refuses to provide the requested information and sends an error code hex05 to the Android phone. This triggers the phone to begin automatically pairing with the responder device. However, the app does not have the ability to stop the pairing process. In fact, the app would not even know of this event. Design flaw 4. Apps do not have the ability to remove suspicious bonds. If an app determines a connection is inappropriate for any reason, it could break it. However, the app cannot remove the bond or the associated generated keys. This means that the app cannot start a new secure pairing process with a bonded device using create bond again. So, what nefarious shenanigans can we manage with those design flaws? Let's start with a simple one. Note that all those exploits require the attacker to be within Bluetooth Low Energy range, which is relatively trivial to achieve in densely packed apartment buildings. Let's say you have a smart scale that your significant other bought you as a hint to lose weight, and you have already paired it to your Android phone via Bluetooth Low Energy. When you step on a scale, the scale turns on, connects to your Android phone, and reports a weight number. I, as your roommate, want to have a little fun with it. I want you to think your weight stays constant despite your efforts. First, I want to make sure the scale no longer responds to your Android phone when it turns on. To accomplish this, I use hacker phone number 1 as an initiator that aggressively listens for device advertisements. A typical Android smartphone might scan for device advertisements once every 5 seconds to save on battery life. I configure hacker phone number 1 to do the same once every, say, 100 milliseconds. This means when a scale turns on, hacker phone number 1 has a much higher likelihood of detecting the scale's advertisements than your phone. Once hacker phone number 1 detects the scale, it masquerades as multiple initiators and sends scan and connection requests non-stop. The number of connections that a responder device can handle is limited, and once hacker phone number 1 exhausts the scale's availability, it can no longer respond to additional scan and connection requests, including legitimate ones made by your phone. Then I use hacker phone number 2 masquerading as the scale and perform a downgrade attack via design flaw 3 against your phone. Hacker phone number 2 sends the advertisement as if it is the scale. Your phone scans it, receives the scan response, and makes a connection request. Since I don't have the LTK stored on your phone during the legitimate pairing process, I cause hacker phone number 2 to follow up with a hex06 pin or key missing error, which causes Bluetooth Low Energy communications to downgrade to plain text. In this case, the error causes your phone to not enforce a secure communication authentication channel. Remember, at this point, the two devices can still communicate, albeit in plain text. Your phone then sends a read request on attribute wait. Hacker phone number 2 has already configured for this attribute to have simple read permission. In other words, hacker phone number 2 implicitly informs your phone that reading this datum does not require secure pairing. Hacker phone number 2 responds to your phone's read request with a fake wait number, and your phone receives it and displays it to your horror. The most insidious part of this attack is that it is silent. The attack does not reset the long-term key your phone stores for the secure pairing with the scale. In other words, unless I'm caught red-handed, there's literally no way for you to know that an attack has occurred unless you have enabled detailed system-level logs. Now, this example seems relatively innocuous, but imagine a medical setting where your doctor is making treatment plans based on data from hijacked medical devices. I'm sure you can see how the damage could be far more troublesome than a few missed fried chicken dinners. What's worse is that if the attacker has physical access to the victim responder device, this attack can be upgraded to a full-fat man-in-the-middle attack. All that needs to happen is for the attacker phone number 1 to be paired to the victim device through the actual pairing process, which requires physical access. Once that is done, hacker phone number 1 and number 2 can act as the middlemen, handling all communications between your phone and the scale. The attack I presented can only be a problem so long as the attacking devices stay active and within range. But what if I'm more mischievous than this? Can I cause persistent damage to systems without physical access using Bluetooth Low Energy exploits? Good news, I can! For instance, I can achieve persistent denial of service using all 4 design flaws mentioned above. Let's say we have the same scale from the previous example, and this time I want to disrupt the connection between your phone and the scale and make it stick even after I move out. First, I use my hacker phone to send out an advertisement to your Android phone. Your phone scans the request and a hacker phone responds with the claimed identity of your scale. Your phone then sends a connection request to which the hacker phone intentionally responds with a Hexo6 pin or key missing error message. The communication immediately downgrades to plain text. Importantly, this process does not terminate the communication since the connection is still active, and a responder device can still send data that do not require authentication. Your phone subsequently attempts to access the attribute wait, which happens to be configured by the hacker phone with encrypted read-write permission. Since an authenticated channel no longer exists due to error Hexo6, the hacker phone responds with a Hexo5 authentication failure error message, which immediately causes your phone to start the pairing process due to design flaw 3. The hacker phone is also configured to appear to have no I/O capabilities so that your Android phone accepts the pairing request without user interaction due to design flaws 1 and 2. This process creates a new long-term key between your phone and the hacker phone, which your phone subsequently uses when it attempts to communicate with your scale again. However, since the long-term key your phone has no longer matches with the long-term key the scale has for your phone, their attempt at communication would enter a deadlock. As mentioned in design flaw 4, since there is no public API for an app to remove the bond, it cannot discard the existing pairing data and restart the pairing process. This deadlock can only be resolved by manually removing the bond in the Android system setting. Now, since you're a tech-savvy person, and if the scale stops reporting wait numbers to your phone, you likely would just pair it again, no big deal. However, it does not take much imagination to see how this can be used for more iniquitous purposes. For instance, a competing retailer could use this exploit to sever all Bluetooth Low Energy connections between Digital E-inked price tags and their command module the night before Black Friday. When the employees come into work just a few hours before store opening, they would discover that it would take forever to go around each and every price tag and manually restore their bonds with the command module. This is not trivial, particularly for larger stores, and would likely result in loss of sales. Now, I don't want to make it appear that it's only Android phones that suffer from Bluetooth Low Energy vulnerabilities. Androids are used simply because they have a much higher market penetration than iOS, and conducting experiments on Android devices is a lot easier thanks to the general openness of the Android platform. iOS developer guidelines state that iOS does not provide a way of enforcing secure pairing protocols either, which makes iOS devices vulnerable to data injection in the same way Android is. However, iOS does not respond to Hexo5 error messages. This is believed to be a problem in iOS since it does not notify the user of the insufficient authentication error either. The communication simply silently fails. Interestingly, this oversight incidentally protects iOS devices from Bluetooth Low Energy downgrade attacks. So, does this mean Bluetooth Low Energy is beyond redemption? Far from it. The smart folks that wrote this paper presented a few countermeasures that can effectively address the design flaws and stop the attacks right in their tracks. To address design flaw 1, allow the app to specify a pairing protocol that includes the I/O capabilities of the responder device. So for instance, when an Android phone tries to pair with a keyboard and a responder device claims that it does not have any means of receiving an input from the user, the OS can know that something fishy is going on and halt the pairing process with an error. To address design flaw 2, allow the app to obtain the negotiated pairing protocol at the earliest possible time. The app knows if the specified pairing protocol is not enforced and can act accordingly, such as serving a security warning to the user or disabling some or all functionalities of the program. To address design flaw 3, enforce the specified pairing protocol when errors occur. If Hexo 5 and Hexo 6 errors are detected, the OS should not automatically downgrade the communication channel to plaintext and/or restart the pairing process. Instead, it should require user interaction for pairing to proceed. Additionally, it should also warn the user if the pairing protocol specified by the app cannot be enforced even if the app is not running at the time. To address design flaw 4, allow the app to remove its own bonded devices whenever needed. For instance, if the app believes that the communication channel between the initiator and the responder has been compromised in any way, it should be able to remove the bond and alert the user. Now, let's see how those countermeasures can prevent the attacks mentioned above. Going back to attack number 1, where my hackerphone number 1 attempts to clog up the active connection capacity for scale, and my hackerphone number 2 attempts to inject fake wait numbers to your app. Since the countermeasures only address the initiator device and not the responder device, the denial of service attack against your scale would still succeed, unfortunately. However, fake data injection would fail. Let's see how. After my hackerphone number 1 successfully occupies your scale, such that it no longer responds to your phone, I use hackerphone number 2 masquerading as the scale and attempting to perform a downgrade attack against your phone. Hackerphone number 2 sends the advertisement as if it is the scale, your phone scans it, receives the scan response, and makes a connection request. Since I don't have the LTK stored on your phone during the legitimate pairing process, I use hackerphone number 2 to follow up with a Hexo 6 pin or key missing error, which causes Bluetooth Low Energy communications to downgrade to plaintext. However, this falls outside the pairing protocol specified by your app. Instead of accepting whatever data are received, the OS immediately notifies you as well as the app, and the app would not log said number and attempt to request for you to repair the devices. Now, let's look at our second attack, where my hackerphone attempts to masquerade as your scale and pair with your Android phone in order to break your existing connection with your scale. First, I use my hackerphone to send an advertisement to your Android phone. Your phone scans the request, and then the hackerphone responds with the claimed identity of your scale. Your phone then sends a connection request and subsequently attempts to access the attribute wait, which happens to be configured by the hackerphone with encrypted read-write permission. Since an authenticated channel no longer exists due to error code Hexo 6, the hackerphone responds with a Hexo 5 insufficient authentication error message. At this point, instead of starting the pairing process automatically as it would without the countermeasures, the OS notifies you that there is an error in an existing bond and asks if you want to pair with the device the phone is currently engaging in active communication. You should immediately know that something fishy is up and terminate the connection. Alternatively, if you happen to not be on the phone, the pairing request simply times out. This way, the original long-term key is preserved, and that next time when your scale wants to submit a wait number to your phone, it can succeed since the bond is not broken. So what do we learn from all this? Bluetooth Classic is very different from Bluetooth Low Energy from a protocol perspective. Bluetooth Low Energy designers have already included a lot of security features, but unfortunately they're not enough to defeat modern basement-dwelling Bitcoin-toting hackers. On both Android and iOS, apps are unable to specify pairing protocols, obtain on-time information during the pairing process, or remove suspicious paired bonds. These issues allow hackers to execute data injection trivially without physical access to any victim device. With physical access, hackers are able to carry out full-on man-in-the-middle attacks. Additionally, mishandling Bluetooth Low Energy errors by Android renders Android devices vulnerable to persistent denial of service attacks where the effects linger even after the attacker loses contact with victim devices. We also learned that effective countermeasures can be implemented reasonably expediently without much complexity. By granting apps abilities to specify pairing protocols, obtain on-time information during the pairing process, and remove suspicious paired bonds, we can effectively prevent data injection attacks described above. Additionally, Hexo 5 and Hexo 6 errors should immediately trigger app notification and manual intervention instead of automatic downgrade and repairing. Doing so can eliminate the possibility of persistent denial of service attacks described above. The paper goes into far more detail about the topics discussed today. I have provided its link in the description. Thanks for watching. I'd like to give special thanks to Catnip Infused Toys, which did not sponsor this video. I used a few of them to keep my cats occupied and away from me while I recorded the voiceover. If you did not hear a single meow, then it means a word. This is an Indian Tribe production, all rights very much reserved.